Alright guys, chapter 22, Electrostatics. Now, the name, as it implies, deals with electricity, the electrode part, but the statics part means still, not moving, right? So we got to start in baby steps. We're going to study electricity in these next two chapters, right? But to do that, we've got to start out with what those electrical charges do when they're not moving, alright? So there's a force there, there's insulators and conductors about who absorbs that charge better, how to charge, electric field, electric energy storage, all that good stuff is what we're going to hit on this chapter. Alright. So electric force is the first thing we're going to talk about. But to do that, you got to know the basic things. Like charges repulse, right? So two positives, like charges, they repulse, push apart from each other. Opposite charges attract, right? Pull together. Okay, so remember back from chapter 11, protons are positive, electrons are negative, neutrons are neutral, right? Okay, so we can have either a force of repulsion or a force of attraction, excuse me. Alright, so here's just a reminder how atoms are formed, right? What they're comprised of, where they all live. Alright, that most atoms are neutral, meaning no charge, net zero charge. But what happens when they are charged? Right? That's when they are an ion, right? And all this is a refresher back from, like I said, chapter 11. Alright, so just refresh yourselves there. Now, charge is special. It's conserved. You can't gain or lose any. You can just transfer it around. Alright? Now, how do we do this? What's actually being transferred? Well, that's the electrons of an atom. Now, some electrons transfer more easily than others. Alright? So we learned from past chapters that electrons live in a cloud surrounding the nucleus, right? Well, the electrons that are on the innermost part of that cloud, closest to the nucleus, well, there's a very strong attraction there, right? Because those electrons are negative, those protons that live in that nucleus are positive. It's a very strong attraction, so you're going to have a really hard time breaking those away to transfer them to something else. But the outside electrons on the outside, they are not as strongly bonded, not as strong of an attraction there, so they could be easily stripped to charge something else. Alright? There's a few examples of how to do that. Alright? Rubbing a glass rod with some silk, or in the wintertime, ladies, combing your hair and you get all that static. Right? What you're doing is stripping electrons off of there. Okay? The charge is conserved. You got the total amount of charge has got to stay the same. It just transfers around. Alright? Now we talked about that force of attraction or repulsion, depending on whether you got positive or negative charges. Alright? Well, Charles Coulomb, was the one who discovered that relationship. Right? He practiced with this, and he saw that that force depended on the charges, right? How much charge you had, right? And specifically the product of those charges, right? So multiplying those two charges together. Now it also depended inversely on the distance between the two charges squared. Alright? So here's that formula right here, right? And the K is just a constant, it's just a constant of proportionality. That's right there, that really big 9,000, that big old number, right? Or if you like scientific notation, right there. Alright, distance is still in meters. Charge, denoted by the Q, is measured in coulombs, hence for the guy, right? Okay? If you ever have to do one of these calculations, don't worry about the charge of the sign, alright? We'll know whether they're repulsed or attracted, right? Okay? So there's a little video to get you familiar with that, a little extra credit point right there, but that's how you calculate the force, right? So remember this inverse squared, right? So if I double the distance between two charges, right? That's 2, but that's 2 squared, so that's 4. And now the 4 will be on the bottom, right? So if I double the distance between two charges, that moves them further apart, That means the attraction should get weaker, right? The force between the two should get weaker. So what you essentially did is you cut the force down by 4, right? Distance increased by 2, right? Distance doubled. Force decreased by 4, right? That inverse relationship there with the square. Be careful with those. Alright, conductors and insulators. We've talked about these before when we talked about heat transfer. It's the same idea. What was a good conductor of heat is also a good conductor of electricity. Right? So metals with their loosely bonded outer electrons are a good conductor. Insulators, steel, rubber, glass, all those tightly bound electrons, not going to transfer them off too fast. Then there's something like silicon, a semiconductor, which is a special group in the middle. Alright? They can transfer that electrical energy and share those electrons better than an insulator, alright, but not quite as good as a conductor, alright, but they can also take the heat, alright, because a lot of heat flows when you're transferring electrons around. Alright, so how do we actually charge something up, right? Well, there's 2 ways. You can charge by friction, right? Rub your socked feet along the carpet, right? Get a good charge, and then, go shock somebody and scare them. That's charging by friction. Alright, so you got to touch to do that, right? As my little cartoon here says. But you can also charge by induction, right? Where it's pretty cool because you don't actually touch anything. Alright? So here we've got this sphere. It's got no net charge, right? Just as many pink positives as it is blue negatives, right? But here we're going to bring this negatively charged rod close. Alright, well that makes the positives zip over here because they're attracted, right? Well, that makes these negatives zip over to the opposite side because they are repulsed. Okay? Well, then we touch the sphere, and guess what? Those electrons are still repulsed. They want to get as far away as they can, so they run off down our finger. And what's left? Completely positively charged ball. Alright? That's induction. Right? You cause the charges to separate, then you give a way for one of the charges to escape, and you're left with a net charge on your object. Alright, here's another way you can do it. Right? We cause the charges to separate, then we just pull them apart, and now we've got 2 charged objects, right? This is induction. It's cool because they don't even touch, and you can still charge them up. Alright, so that charge separation that we were just talking about with induction, that's got a special name, right? That's polarization, charge polarization, right? And what's happening inside there is all the positives are attracted in the picture here to that negative charge rod, right? Remember, opposites attract. And all the ones that are repulsed, the electrons, they move on to the other side, so you get that separation, right? That's polarization, right? And that can happen within an atom itself, like here in the picture, or with something like the spheres, like we just had in the previous slide. Alright? Now this is pretty cool. You can even try this at home. If we have time, we might try this in the lab. But you get a balloon, rub it on your hair, alright? That's going to make your hair all staticky, but it's going to charge the balloon up too. Go stick that balloon on the wall. It will cause polarization within the wall, alright? And then this force of attraction, alright, is so strong that the balloon will actually stick there. It will stick, alright? Okay, and Coulomb's law governs the strength of that attraction, right, as we talked about in the previous slides. Alright, well, our charged particles are feeling this force of attraction before they even touch, right? You bring a positive and a negative close together, they're going to feel the attraction before they ever touch, right? So there's got to be some kind of force field or something surrounding all of these charges, right, to make them feel the force before they touch, right? This force field is called the electric field, right? And the electric field depends on the strength of the force and the charge, right? You can see your equation right here. Electric field denoted by the big E, force divided by the charge, okay? And you can see some pictures of it here, all right? And we're going to just show you in just a second how to draw these, how to know what directions they go, Alright, and there's a little video to catch too. Alright, so how do you know the direction? Well, we pretend like we've got a little tiny positive test charge, so tiny that no other charge can really see it or feel it. Alright? Okay, so we're going to take that tiny test charge and we are going to bring it close to this big positive charge we got right here. Right? We're going to bring it close. Now, I've got a positive in my fingers that I'm bringing close to this big positive. So, that's the same charge, right? Positive, positive. So, they are repulsed. So, when I let my little charge go, what's it going to do? Zip. As far away from that positive charge as it can. Boom. That's how you draw your electric field. The electric field will go in the same direction as the force on that little tiny charge. Alright? Same thing over here. We got a negative charge now. I'm bring my little tiny charge in there. Let it go. Zoom. It's attracted. It's going to zip right in there. Okay? That's how you draw your electric fields. Okay? And it also gives you an idea of how things are going to move. Okay? Well, there's a lot of energy moving around, right? These electrons getting transferred, zipping around, right? All these force fields and stuff. So there's got to be energy here. Right? Was there a way we can harness it, store it, keep it? Right? There is. It's called a capacitor. Alright? And we'll get to that in just a second. We've got to do the legwork first. Alright? So imagine we've got this positive charge bar over here, this negative bar over here. We put our tiny little test charge right here and we just hold it there, right? It's hard. It's hard. We're doing some work moving it from the negative bar over to the positive bar. Because it's attracted to the negative, so they don't want to go. So we're doing some hard work to move it over there, right? Well, recall from past chapters, the amount of work done is equal to the amount of potential energy now stored at that point. Right? So this amount of electric potential is given by this equation right here. Potential energy divided by the charge. Right? That's called your electric potential, or as we more commonly know it as voltage. Alright? Voltage is measured in volts, alright, which is joules per charge. So you got joules of potential energy over coulombs of charge. Alright? Catch those videos. They got great animations and pictures in there. Alright? So, you see those signs that say danger, high voltage. Well, it's not the voltage that can harm you. It's the charge, right? It's how much energy is in that charge, alright? So read through this slide and get that understanding, right, for your safety. Alright, so now here's the capacitor, right? We're going to get these two plates and we're going to hook them up to our battery right here. We're going to let all the charge flow out of the battery and fill up these plates, okay? Once they're full up and that battery is essentially empty, we can unhook them, unhook the wires, and now we've got all that energy stored in there that we can use later. We can take these wires and hook them up to something else and use it later. Alright? So in here it tells you how the capacitor works and how you can get more charge in your capacitor to store more energy. Alright? Very cool things. Here's some pictures of capacitors, what they would look like. Alright? And a little detail about how they're made. Okay? Do not touch a capacitor ever because you don't know if it's charged or not, and you do not want it discharging through you. Alright? So be safe. Read your chapter, read through these, and I will talk with you guys later.